titles for these shows because we sort of talk so often about some of the same topics that I'm, I'm running out of new titles. We okay. Okay, we I think are live now. They've changed the interface on Zoom for no reason. They don't need to, but they just want to keep us on our toes. All right, we, I think, are live. Okay. Hi, I'm Meta Spencer. Today, let's go back to the ocean and have another look at this thing called ocean iron fertilization. This is a topic we've talked about before, and I expect we'll probably talk about it again because it's a very important topic of conversation. It's something that people are putting forward as potentially helping solve global warming. And there are a lot of people who certainly don't agree with that idea. So it is controversial. And therefore, when we have a big controversy like that, we ought to take our time and unpack it and explore it and look at it from several different angles. So every time we hold a conversation about this, and I think this must be about the third that I've held on ocean iron fertilization, we always come at it from a different angle, or we find a different person to comment, and you never know what's going to come out of it. So I have two guests today. Peter Fikoski I'll name first because it's easy to handle. It's so easy for me to tell you a little bit about Peter because he's so often with me. He's such a generous person with his time, and he knows so much that I draw on Peter every few weeks. And I think I actually invited you last week too, Peter. Peter Fikoski lives in Silicon Valley, and he is a sort of an engineer, so I mean originally, and at MIT, and really is interested in climate repair. So he's actually been funding research on climate repair. And I don't know what more to say, except that we will get into it, I'm sure, in a few minutes. And I'm saving my big introduction for Kate Moran, who is, I presume you're in Victoria, British Columbia. Is that where you're located now, Kate?
Yes, it is. Yes.
Good. And your name is really Catherine with a K, but I see you call yourself Kate a lot, right? So
Yes.
we can call you Kate?
Yes, please.
Okay, very good. And Kate has brought her two lovely French poodles to our conversation. And I'm delighted to invite them to participate. I don't quite know how they'll do that, but I'm sure we will hear from them, or at least enjoy their presence. Kate is the president and CEO of Ocean Networks Canada, which was an initiative, she tells me, of the University of Victoria. It is now, I guess, an independent NGO or something of that kind. And it definitely deals with topics that are related to the oceans. I've looked at your website, Kate, and there are a big staff of smart people doing good things. So I'm glad that we'll have a chance to get acquainted. I noticed in your bio that you had at one point been seconded when you were at the University of Rhode Island. Apparently you you worked on the Arctic, on polar and oceanography and climate issues, and you were seconded to the White House to the Office of Science and Technology Policy, which sounds like fun. And I don't know when that happened, but it would be worth kind of hearing a little account of what it would be like to work in the White House on climate. I wish we all had several people there, friends in the White House, which I don't think we do yet. So hello, Kate, and welcome. And tell us, if you will, a little bit about your institute, because I didn't know about it, and now I want to find out more. Behind you, there's a wonderful mural. I don't know, is that your office wall or is that your living room?
That's it. This is in my office. Yeah, this is one of our Zoom rooms, and we just have a display of a representation of I can explain it. The
Uh-huh.
representation of
Well,
what we
go
do.
ahead.
Sure.
Tell us about the map, and
Okay.
but mostly tell us first a little bit about your organization.
Okay, so Ocean Networks Canada, we're a nonprofit. Here in British Columbia, they're called societies, and we were established by the University of Victoria to operate ocean infrastructure for the purpose of observing the ocean. Here at the University of Victoria, there were two maverick scientists who decided to develop and install what they call telecommunication cable-based ocean observing. And that started on the west coast of Canada off of Vancouver Island, these two systems that were called Neptune and Venus. And we're basically using telecommunication cables to provide power and high bandwidth internet connectivity to sensor systems that sit on the seafloor, beneath the seafloor, in the water column. And since that time, these two mavericks, as I took over as president, we have taken the infrastructure that was built on the west coast of Canada and now are partnering mainly with Indigenous coastal communities to install and operate observing systems on all three coasts of Canada. And so that's what this map is, just showing you dashed lines of that, essentially the data flow of these systems from all parts of Canada, Canada's coastline and offshore. And we measure everything that's possible in the ocean: chemistry, physics, biology, geology. And now we have three major goals as an organization. One is to advance ocean observing because it's the least understood part of our planet. Our second goal is to develop data and data products that enhance knowledge of the ocean and help people make decisions about the ocean. And our third goal is really related to what you're interested in. We are working on climate actions, both mitigation and adaptation. And so although we are agnostic to which ocean technology solution, for example, carbon dioxide removal, is the best, we have a platform to take technologies that are early technology, to advance them in a real ocean environment, to assess their efficacy, to develop monitoring, reporting, and verification, and to really see essentially the balance of risk versus benefit. And that's what we're dedicated to doing in terms of ocean-based carbon dioxide removal.
How wonderful. That means you've actually given some thought to both the risks and the benefits. And we can get into making some comparisons about that, right? Maybe you've looked at various proposed technologies, because there's a variety of, must be 10 or 12 different things on, that are proposed every now and then as ways of curing our climate crisis. But it would be wonderful to have numbers that actually could help us understand what how much weight and probability to give to all these things. Is that possible using the numbers that are generated on that thing on your wall?
Well, we're just in the early stages of doing these experiments, but yes, that's the ultimate goal, is to really assess those things. And for the most part, so I was part of the U.S. National Academy study on ocean-based carbon dioxide removal research that was published a couple of years ago. And so that laid out a plan for how you conduct research to assess these. At that time, it was defined as 6 different ocean-based carbon dioxide removal solutions. So I'm not a specific expert in any one of them, but an expert in understanding how we can conduct research to understand them better and make decisions about them. There's one other project that I'm leading right now, which is called Solid Carbon. It's not the same as the topic you're talking about here, but over the past 7 years, I've grown a research consortium to look at this project called Solid Carbon, which ultimately would combine direct air capture of CO2 on an ocean platform powered by renewables, taking that that air captured CO2, pumping it through the water column and injecting it into subsea floor basalt. Here at Ocean Networks Canada, we are lucky to be able to monitor in real time one of the best understood ocean basalt locations on the planet. And because of that, we are continuing to secure funding to do a demonstration because we do think that this could be one of the largest and safest approaches for carbon dioxide removal.
Okay, you've already named something that I have never heard of before and I want to know more about. Peter, do you know what she's talking about? A solid carbon? This platform thing? Have you ever heard of that before?
I've heard mention of it in the ocean. I believe it's the same idea as the Iceland carb fix and what's it called? Climeworks.
Climeworks,
Yeah.
yes. Yes.
Oh, so you will be, you have big fans and you suck the air through and capture the carbon and then you want to, now tell me,
yeah, let me just
start
explain.
at the top with this.
Yeah,
because I really want to know about it. I've heard of it.
Yeah, so Peter's exactly right. We're really building upon the research and the actual industrial development that's happening in Iceland. And that was, oh gosh, I think Peter, 8 years ago or so, technologists and scientists in Iceland. Iceland is a piece of basalt, ocean basalt, relatively young. And they injected CO2 into that basalt. And they then demonstrated that within 2 years it became rock. Now, the reason that we're interested in our location off of Canada's west coast is because over 95% of the type of basalt that is amenable to this approach, reacting with the basalt, so CO2 is permanently removed. 95% is in the ocean. And so and the reason that Ocean Networks Canada got involved in this, because I had a colleague at Columbia University who is a leading researcher in this area. And he contacted me to say, we need to actually demonstrate and do feasibility studies at your location. And it's called Cascadia Basin. We know from just looking at previous scientific ocean drilling here in Cascadia Basin that the capacity for this kind of basin is over 100 gigatons. We think it could be as high as 700 gigatons, and in just one ocean basaltic basin. Now, we as an organization are not doing research on direct air capture. We're pleased to see the US Inflation Reduction Act investing in direct air capture, because as that advances and costs get reduced and it gets developed, which hopefully it will, but I'm not an expert in that, we want to be sure we have the sequestration locations that are permanent. What the oil and gas sector is doing is proposing to put these into sedimentary basins, which are not permanent solutions. And so that's why we want to advance this.
Tell me, excuse me, sedimentary basins.
Yes.
I need help with that.
That's where oil and gas
land, not you're talking about ocean deposits.
But both. I mean, the oil and gas sector is proposing to, and they are doing it in some locations, sequestering CO2 into sedimentary basins. It's where oil and gas is. So it's really, and that you need to forever monitor them. And as many of us know, the oil and gas sector is not well known for maintaining their infrastructure for decades and decades. So it's really, our goal is to really make it a foolproof sequestration solution. And that's why we're researching solid carbon. So sorry, I'm way off topic then.
No, you're not. I mean, we don't have to stick on any topic. Our topic is how we're going to save the world. And so that's pretty broad. And I am very interested in this notion. Now, I've had a lot of shows with people who want to do enhanced rock weathering and using primarily basalt. And I had the impression that basalt, there's no shortage. It's like all over the place. You don't have any problem. You just look out the window and you're probably looking at basalt. But you're saying that most of that you have to pick and choose where your location is at. Is that right? And then you have a particular choice location.
I don't know where you're located, but the Palisades.
I'm in Toronto.
Oh, okay. So yes, there are so most of the land-based basalt is quite old. And so there's been millions and millions of years of reactions that have taken place to fill most of the pore spaces. And so if you want to use that basalt, you'd have to frack. Now that makes no sense. And there's a ton of ocean basalt near spreading centers that's young. Young is 20 million years old and younger. And so it's really that ocean basalt is high porosity, ready for reactivity with carbon dioxide. And so it sits in ocean spaces. I have to let a poodle out just.
All right. Okay. Well, I'm curious about whether or not the challenge, I don't know whether you can hear me, as whether or not the main challenge is in finding a place to put the stuff, or in being able to efficiently collect the carbon out of the atmosphere in the first place. I mean, I think I assumed that there wouldn't be any problem putting it away if once you figured out how to get hold of it, suck it out of the air, do it efficiently. And I haven't pursued that so much myself because I thought, I don't think that's very probable. I think that doesn't sound as promising as a lot of the other things that people are proposing. Peter, what do you think?
Well, the goal, of course, is very critical. So I think all of us want to leave our children with a safe climate like we were given. And doing that, as Kate sort of suggested, is going to be about 1,000 gigatons of CO2 removed at first, and then another maybe half of that more over the coming decades as the ocean degasses what it's absorbed. And once we're clear on the goal, then how to do it, of course, becomes the question. And it's important to collect it, and it's important to store it. I think most people are realizing that it's becoming very urgent with all the wildfires and the storms and the collapse of the Atlantic current and so on, that we don't have 100 years, we don't have 50 years, that serious things are happening right now, and they're getting increasingly serious year by year. And so I have to say I do have an opinion on this, which is that we should do the fastest thing that's been proven. And that's to do to replicate what nature has done before ice ages, because we know our planet goes through ice ages. We know that the CO2 that's been removed before ice ages is the amount that we need to remove to get back to what it was when we were young, 50 or 100 years ago. And hopefully none of us are 100 years.
Getting there.
That's right. And so we want to so I'm a Silicon Valley entrepreneur. My training is in astrophysics, actually, and then being an entrepreneur, I had to get very good at engineering and project management. And so my group decided long ago to create Restoring a Safe Climate. You call it repair. I like restore because restore has a set goal to what it was when we were young, at least. And
well, look, one of the things we are going to talk about ocean iron fertilization, but my question right off the bat is, how much priority would you assign to that? If you have just a limited amount of money and you can only invest, let's hope this never happens, that you can only invest in one new technological solution, or even exploring the potential of some of the various technologies that are available now, which one would you pick and why? And I wonder whether you two would agree on your assessment of what is the most promising. I would not have picked a direct air capture. my assumption is, based on just, running about 50 shows about this kind of thing, that it's not the most, I don't know. I think there are probably other ways of quicker getting some effect. But let's ask our guest, Kate, which one, right now, if you were in charge of deciding what to bet on, what would you pick?
Well, I don't pick. I mean, we need to invest in everything. I'm sorry that we don't have a magic ball to understand what's going to happen. And so and so that's why we're working on ocean-based carbon dioxide removal. That's why we're working on solid carbon. We need to invest in the research, and it's pittance compared to the subsidies to the oil and gas sector. So I'm not going to pick anything. I'm going to do everything I can to advance the research so we can make decisions. That's my position. And I don't want to have these solutions fight against each other. It's just stupid to do that, basically.
Good.
I also want to say something about repair. So I've done paleoceanography, and Peter, you probably know that, but what we are doing right now in terms of the emissions into the CO2 is like a meteorite impact to the planet. And when that kind of thing happens, the planet changes. So I think we don't know what the planet's going to be like because of that. The rate at which it's all a rate problem. And right now, as I see it, I'm kind of excited because I'm in the middle of a meteorite impact on the planet. and I'm able to watch it. And so I don't think it's a repair. I think it's how do we live in this new world of post human meteorite.
So it's not, he likes the word restoration, but we're not gonna quarrel between restoration and repair.
Right.
Question, your language is going to be future oriented, really.
It's survivability. It's human survivability, because I also disagree the planet's going to be just fine. It's can we live on it as humans and have a rich biodiversity? That really is the position. That's the issue, not that the planet. It'll be just fine.
Yeah, after we have been exterminated, it'll feel a lot better.
Yes.
That's right.
Yeah.
Okay. Well, let's talk about ocean iron fertilization.
Okay.
Since we
maybe I could weigh in, because not being an academic, I am entitled to having an opinion. And being a Silicon Valley guy, I really like goals. And I think the three of us lived through the moon landing, where President Kennedy said, we're going to land a man on the moon and bring him back safely by the end of the decade. And it was clearly impossible in 1961. I mean, it was conceivably possible, but so was anything. But we did not know how to do it. The scientific community opposed it because it was a waste of money. But I'm a fan of JFK. And so what my team did, Kate, is we said, well, the first step was to figure out for whom is the climate a problem. And we realized that for science, as you said, it is fascinating.
Yes.
So it's not a problem for science, but it's a problem for us as parents and grandparents, because we actually do want our children to have to live on a beautiful planet like we did. And so then as an engineer, I said, how would we, let me just move your picture up so I'm looking at you. Okay. So we asked, if we were to restore it, by when would we need to do it? And we figured by 2050, because even 10 years ago, it was very clear after 2050, our planet will be totally different, and bringing it back would be quite unlikely. And then by 2050, what do we need? Well, as humans, what we want is to have the same CO2 that humans have survived long term. And that was 300 parts per million. In theory, we'll be okay at 350, but as parents, we don't like in theory for our kids. If someone has a new plane, they say, in theory, I think it flies fine. We put our kids on the one that's flown thousands of times. Right. So that's the origin of 300 parts per million by 2050. It's that simple, no more detail than that.
That makes sense. That totally makes sense. I don't disagree at all with that. That's a great
Yeah.
explanation.
And then working again with the moonshot, they spent a long time trying to figure out how to do it. They finally, the way they actually figured out how to do the moon lander and all the orbiter and lander and return capsule was they reverse engineered it. They said, okay, good. We're on our way back from the moon. What happened before this? And when
Mhm.
they worked backwards, it was clear there was no other way to do it than,
Interesting.
yeah.
Yeah.
And so
Huh.
working backwards from CO2 is falling below 300 in the year 2050, we said, okay, what would happen? Well, clearly there were two or three methods operating because in any important system, you always have the main system and two backups, always, the airplanes and so on, submarines and so on. And then the CO2 will be being removed at about 60 gigatons per year. You can divide 1,000 gigatons by 50 years and add 10 gigatons per year for various reasons. And then we just ran that through the standard modeling that the magic modeling that IPCC uses, and 60 gigatons a year. And then we said, okay, good. We know what the rate is. We know that we have a primary and two backups. And then what do we do? Well, in engineering, what we always do is we say, well, how has this problem been solved in the past? And of course, the first thing that I think the three of us thought about, because was like, oh, we've had submarines for 100 years. And so that's where the direct air capture comes from. Direct air capture is derived right from the submarines. But then really it was around in the 1990s, early 90s, when John Martin came up with well, first of all, we had the ice cores. So we understood much more about the CO2 levels going up and down before ice ages. Because when I was a kid, we didn't understand that at all. But again, once we got to the Kate, you could fill in the details, but you get the general idea.
Mhm.
That is really just the last 3 decades that we said, oh, we understand how ice ages work, and oh, we could actually replicate them because the amount of iron involved is, it's at worst $1 billion worth of iron, which is a trivial amount of money. The cost of distributing iron dust is extremely low. We have to figure out where to do it and how and so on, but
Oh,
that's,
excuse me now. Now I hear you talking about something that sort of sounds like ocean iron fertilization. Up to
yes,
this point, I didn't hear that. But
Yeah.
now
yes,
you're into that modality of working, right?
yes, yeah.
Mhm.
All
Yeah,
right.
Yeah.
because again, it's great having Kate here because I'm guessing we're pretty close to the same age, and probably went through the same thing. When I was an undergraduate in the mid '70s, I read about global warming, and my mind went to modifying, improved how submarines get CO2 out of the air because we didn't know how ice ages did. And then my
Mhm.
brain was pretty much set in concrete
Mhm.
after that. So by the time John Martin told us exactly how to do it, my mind was already set on the direct air capture.
Mhm.
And really, it was just the last 6 years that I said, okay, delete everything because we're now in a total emergency. Um, how would you do it now? I was, oh, and let me show you my little graph here, Kate. Um, share my little graph. And so two graphs. This one, Kate's seen this 1,000 times. For the audience who's seen me, they've seen it 3 or 4 times. This is sea level over the last million years, and the warm periods, the CO2 levels here are about 280. The highest level we've ever survived right here is 300. And you can see it going up and down, up and down. And we need to remove roughly the same amount of CO2 as was removed during the ice ages. Now, what's interesting is, and I really have just been talking about this in the last year. If you take the Keeling curve, which is CO2, this is being measured at the top of a mountain in Hawaii. You can see the CO2 is steadily going up as we keep burning more coal and gas and and other fossil fuels. And then if you look at the period around Mount Pinatubo eruption in 91, that was here. The following year, we had net zero for 14 months. And that really caught my attention because I realized, oh my God, that's what we've been wanting to do. And we've been oblivious because when this happened, we sort of were just beginning to wrap our heads around how ice ages work. And so we thought it was a blip, but now it's 30 years later, and you can see the CO2. So this is averaging it out in a way from that NASA and NOAA do. And you can see a steady increase, gradually increasing as the population increases. And then here's the net zero for a year in 92. And then the CO2 continues up at about the same pace. And you get this blip here, which is the El Nino, huge El Nino in 1998 with a dip before it, which is what tends to happen. You can see there's an El Nino here. I believe, I don't remember which El Nino that was, but they average out over about 10 years. Anyway, so we have a demonstration where we can actually replicate what's already been done.
Hold on now, because I want to make sure I'm following you, and I'm not sure. I think I'm not. The people talk about Pinatubo only as when they're trying to argue about SAI, stratospheric aerosol injection. That is spraying. Usually, they talk about sulfur into the stratosphere. Now, what you're doing there, I don't think you're talking about SAI. And so how does this Pinatubo event relate to carbon reduction technologies? Because Kate's been talking about carbon reduction or carbon removal.
Yes.
And I think you are driving at that, although I don't think you've used the word. But those are two different modalities. Reflecting sunshine back into space is different from removing carbon dioxide from the atmosphere or the ocean, right?
Yeah, but I think Peter's exactly right. I mean, all the ice core data also supports Peter's interpretation of what's going on here, because when you look at the ice core data, you can see that when there's increased dust, that's been deposited in these ice cores, it means that there has to be, and the CO2 changes in those, so there's direct evidence. And so you can see that this is likely an ocean fertilization effect, where you're providing nutrients to areas of the ocean where there's not enough nutrients to grow phytoplankton, and then they absorb CO2, etc. So, I mean, there's a lot of evidence from the geologic record to support that interpretation.
Yeah.
Rather than the atmospheric where you're actually it's a temperature effect that I never heard the SAI acronym before, but thank you for that.
Right.
Sorry, you didn't hear people talking about Pinatubo in connection with SAI?
No, I have. I never hadn't heard. I'm an acronym. I try to get rid of acronyms, so I never heard the acronym. Thank you for that. Now I know.
I think, unfortunately, when people talk about geoengineering, 99% of the time, if they're not a real climatologist or somebody with expertise, the only thing they're really referring to is strategic or stratospheric aerosol injection, this spraying of or releasing of sulfur, which scares a lot of people because all kinds of bad things might happen or theoretically could happen as a result. Therefore, I think that's the reason for the extreme opposition that we hear to geoengineering, is that's what the people think that it is, nothing else. And of course it is, there's a lot more that's possible, and probably the risks and the benefits and the potential vary all over the place from one to another. But anyway, so I interrupted Peter. I'm sorry. You can get back to work now, Peter.
Yes. So yeah. So when Pinatubo erupted, there were two phenomena. One of them was the dust in the stratosphere, the sulfates in the stratosphere, which reflected sunlight back into space, cooled the planet by 0.5 degrees C. The second one was there was gigatons of dust that were dumped into the nearby ocean. And there was a big windstorm, a big cyclone right at the same time, and it blew all the dust, most of the dust into the ocean. And so it's a good hypothesis that provided nutrients for phytoplankton growth.
Right.
And
Yeah.
it turns out that there was a downwelling eddy that's always roughly in the same spot there. And there's a hypothesis that something about the downwelling brought the detritus from whatever bloom there was deep into the ocean where there's no oxygen. And
Lower, just lower oxygen. Yeah.
Yeah, right, yeah, exactly. Yeah. I thank God for scientists. Poetically, no oxygen. Scientifically, very low oxygen.
Yeah. Yes.
And
yeah. So I think I think it's, and I agree. It's, there's other phenomena, natural phenomena that are examples, like dust from Africa into the Atlantic Ocean. So these are well established connections that mean that it's worth pursuing, because we know them. They happen in the geologic record, for example, or in these kind of events that we just described.
In discussing your institution, you mentioned having some sort of institutional connection to the indigenous people's activities.
That's right.
And now my impression is that the first real experiment in ocean fertilization was done at the request of the Haida Indians to improve their fishery stock. And that may, I don't know whether you would say that as a result, or that is still true, that the indigenous people are more likely to be open to considering the value and maybe supporting ocean fertilization. Or because, the average person, if you ask, most people say, "Woo, don't go there, that's dangerous." But if they had, and I understand that the experiment worked, this thing with Russ George a number of years ago, that it worked, and they did later have a huge increase in the salmon the next year. And so maybe they, they were happy that it worked, and maybe they'd like to have it happen some more. Do you think there's any tendency for the indigenous leaders to support exploration of this and any other potential climate? I don't know whether I want to use the word repair, restoration, or whatever term you use.
Solution. How about a solution might be the best word. Let me just come back to that. That really wasn't the first experiment. I mean, the first experiments, if Anya Waite were here, she did her PhD on experiments in the Southern Ocean of iron fertilization. So there's been scientific experiments earlier than that, but that was more of a, I would call it a rogue event that, didn't go through the process of, talking about it. And so it was just before I came here. And I would say that the indigenous community, as you probably know, are incredibly diverse, including in British Columbia, and they're all different. So every community we talk to and work with has different priorities and different views. So I can't speak for them, but I don't hear any kind of rousing support for solutions at this time. So for example, with solid carbon, we have a social scientist from the University of British Columbia who has been conducting workshops with coastal indigenous communities. And there's questions still. And so I think that it's important to conduct research on the social side in parallel with any of these solutions, because if we don't do that, the knowledge about what we're talking about here does not get shared, so that there's an understanding of the risks and the benefits. And so I'm advocating as much as I can for ensuring that we conduct that research as well with any of these solutions. So we now have a new partnership with the Haida Nation that's related to measuring changes in their offshore areas, but also to work on measuring noise to reduce the impact of noise on marine mammals. So as we have more discussions with them, we can probably ask those questions, but I don't know the status right now of that particular topic.
Mhm.
Now, Meta, if we can, first of all, it's important to see that there are benefits to the indigenous peoples improving the health of the ocean. And in terms of having an opinion about what we should do now and soon, on the one hand, the cost of restoring a safe CO2 level using nature's method, which is the ocean fertilization. I'm American, so it comes out to about a penny a day per American. So it's very, very inexpensive because it's been done before. On the other hand, it's not permanent, right? The ice ages come and they go. And the work that Kate is doing over hundreds of years is going to be very important because we don't want that the carbon that we would get sequestered into the ocean, it's not going to be there forever. And so we are going to have to sequester it into rock. And over the years before I wrapped my brain around ocean fertilization, I was looking into exactly what Kate is working on, which is we know how to get CO2 out of the air. It's very expensive still, but the price will go down eventually. It always does, just not fast enough to save our to save our civilization if we went that way. So, but we do want to continue developing the direct air capture over the next many decades because we are going to need that. And sequestering it into basalt, I don't know why it gets so little discussion, but really that is the only way it's going to happen. And it's great to say what you said, that I hadn't heard the 800 gigatons, but that in one spot, that's amazing.
About 700. Yeah, 700 is our maximum. But we'll know more once we do a demonstration. So we're just trying to get funds right now to just do an injection, just like they did in Iceland, and then begin. Hopefully, when we do that, there'll be just more, press about it and talking about it. And we're working with CarbFix and Climeworks too, because they're interested in this too, in taking that and moving it to other parts of the planet.
Yeah. So we want to do both. We want the quick solution, which is replicating what nature does, and we also want to invest in the long-term solution to permanently sequester it in the rock.
Yeah, and of course, the classic, example of the minerals into the ocean is the uplift of the Himalayas. Those longer rates. Those two were part of that. It's all part of that so-called natural solutions that have changed our climate over time.
Yeah, and then one of the interesting things, Kate, is we did a cost analysis, so we know what in Iceland the cost is about $1,000 a ton of CO2. And then by contrast, using the 2012 case as a test, what does it cost to distribute the iron dust at 100 tons at a time? And that came out to 1 to 3 cents per ton of CO2. So you have a sort of a 10 or 30,000 to 1 price cost difference. And so that gives you an idea of why you want to focus on the low cost thing, which has been tested by nature. At the same time, we're also improving the long-term.
Wait, back up, because when you say you want to go with the low cost thing that's been done by nature, which are you referring to?
That's ocean fertilization.
Ocean fertilization. Yeah. Okay. Well, Kate, would you agree with him or?
Well, I think it's low cost for sure. This paper just came out in Nature a few months ago that combines electrochemical ocean iron fertilization and alkalinity enhancement, which is interesting. Have you seen that paper, Peter?
I haven't read it. I've seen it.
Yeah, they were estimating iron fertilization, about in dollars per ton, but that's still, it's all small. You know, it
Yes.
doesn't, it's as one of my staff used to say, it's in the noise floor.
Yes,
So,
yeah.
Yeah.
Well, one of the
And
nice
I would love to, I've been talking with Ken Bustler. Have you been talking to Ken, Peter? Yeah, because I think that an experiment that is planned and talked about, and social scientists are involved, would be really a good thing to do. And we have a location off our coast that called it's called line P. Are you familiar with these lines, Peter? So in the world of oceanography, the first longitudinal studies were done by having oceanographic vessels go from land-based to the old weather stations. So Station Pop is off the west coast of Canada.
Oh,
And
right.
so Fisheries and Oceans Canada has been for over 60 years, 4 times a year, doing these transects, collecting water column data along the line. There's other parts of the ocean, but this is a place where there was an experiment that we just talked about. And it goes from a coastal area to the open ocean. So from high productivity areas to low productivity areas. And we think that we should begin to put sediment traps along line P, get the baseline information, and then conduct small scale experiments along this line. And then just to begin to just demonstrate it, to raise the profile, show that it works. And it would be a relatively low cost experiment, but with I'm guessing there'd be good public acceptance of it because it would be planned and shared. And anyway, so that's what we've been talking about one thing we could begin to do pretty easily, like right away, if there was interest.
If you don't mind, I think we ought to mention
I need to
any.
leave in about 3 minutes.
Okay.
Yeah, I have a hard stop at 10:30. So, or
I want us to at least mention any of the negative side effects that some people worry about.
Well, they worry about harmful algal blooms. Right.
Sorry?
I mean, basically, there's a worry that you would create harmful algal blooms, from this. So,
well, also the question of whether or not these things, when they do sink you want it to sequester carbon by falling to the bottom of the ocean. And I understand they don't necessarily get very far down, and they might come back up or something. Do we know that phytoplankton will actually remove CO2 by falling to the bottom of the ocean and staying there?
Well, that's what an experiment would help to answer those questions. I mean, because phytoplankton are the base of the food web, so of course critters in the mid-water column would likely want to eat them, and then you'd have this. So yeah, it's understanding these rates and the amount of So experiments would be very helpful, I think, in terms of answering the questions you have. Where in the world would it be best done? Everyone says Southern Ocean. Okay. Maybe we do an experiment there. Anyway, so Anya Wade is actually, too bad she wasn't here because she did her PhD on this topic. So
how much, if I can let Peter finish and then go, I'll hang on to you a bit longer, Kate, and interrogate you, because if you're in a rush, Peter, what's up?
Well, Kate's also in a rush. So a couple things. One is with the ice ages, the carbon doesn't fall to the seafloor. If it did, then it's hard to imagine how you would get the carbon back out at the end of the ice age when the planet warms. So I think the common belief is that the carbon is in what they call dissolved inorganic carbon, carbonates and bicarbonates. And so
well, the ice ages are related to Milankovitch cycles, really. So
well, the trigger is, but then the Milankovitch cycle doesn't affect CO2. It affects whether you're getting more sunlight on land or in the ocean, essentially. When the Earth is closer to.
I think we need another hour of conversation.
Yeah, in any case, but my point is that it's the issue isn't so much the carbon on the seafloor. The issue is just replicate what's going on.
Yeah.
Okay, we're doing a project working with the Philippine Coast Guard to start replicate what happened in 1992, because if you look at the other volcanoes, that caused half-degree warmings, so
Mm.
1980, 63, and of
Yeah.
course 1883. Those don't have the CO2 dip that Pinatubo does.
Okay.
And
Okay.
so that's why we're doing it in the Philippines, because that's where it happened. We want to replicate it there.
Oh, interesting. Oh, I'll look forward to hearing the results of that.
And the final part with that is the hypothesis now is that there was that there was the downwelling to sequester it long term, and then there was enough iron to for a long enough time to get the nitrogen fixing bacteria to reduce the nitrogen, because quickly after you have iron, nitrogen becomes a limiting factor. But of course, there's nitrogen if you can fix it. And so our testing is going to be to demonstrate whether or not we actually can expand the nitrogen fixing process.
Perfect. Oh, that's interesting.
Yeah. And with that, I need to go.
Yeah. Okay. Nice to meet you, Peter. Thank you so much for the conversation. Yeah.
Oh, this is great. Hope to talk to you later, Kate.
Okay.
Okay. Thank you, Peter. As usual. I appreciate it.
I have to leave in about a minute and a half too. So.
Oh, well, okay. Then I don't want to detain you, but because I'm not sure I could start up a whole new topic and pursue it more than in a cursory way. It's been great fun and very, very interesting and valuable. So I'm delighted to get acquainted with you and know that you're doing all these good things. I'll try to follow a little bit more of what you the numbers that you generate from this activity.
Yeah, well, thanks for the invitation. And if you come to Victoria, come and visit us.
Thank you. I would love to, but I probably won't. But at any rate, it's nice to meet you.
Okay.
It's nice to have you on our side.